Right, ladies and gentlemen, good morning. Welcome to our full Q&A session for MOW 217. If you have any questions that would like to ask with MOW, you can either do it via the chat messages, or you can also just raise your hand if you want to use audio. Just with regards to some logistics as well, this session will be recorded, so I'll also make a YouTube video link available once we're done with the session, and you can also review it on YouTube.
Okay, so Mr. Beeren's question, it will be all the work from for the whole semester. Everything will be included in the scope of the exam.
Right. And then Ms. Charlotte, with regards to your question, I think it's with the Excel spreadsheet we went through yesterday, just with regards to some tolerance stack-up analyses. So I just want to head over to the lecture notes that we looked at for that. Then I'll share my screen and we can go through the example over there. Okay, so I think to describe the W min and W max, just quickly going to head back to the question that we actually looked at. So this was example 1.7 on slide 67 over here, or 58. I see there is a discrepancy between the slide numbers, but this is the example we looked at. So just to quickly go through the question again, it says that we have some sort of a shouldered screw that contains three hollow right circular cylindrical bits on the screw before a nut is then tightened against the shoulder. So over here, we'll probably have some sort of a nut that's going to sit over there. So to then sustain the function, the gap W must equal or exceed 0.08 millimeters. The parts in the assembly depicted in figure 110 then have dimensions and tolerances that are also given over here. So we can see we have equal bilateral tolerances for all of them. Then with regards to the actual question, it states over here that all parts except the part with the dimension D are supplied by the vendors. The part containing the dimension D is made in-house, and we need to estimate the mean and its tolerance of the gap W. So what basic dimension as well for D will then ensure that we get W greater than or equal to 0.08. Right, so I'm just going to take this screenshot over here, and then I'm going to copy it over to maybe a new Excel spreadsheet. So I'm just going to open Excel on my side. Okay, so now that we know what the question is, now we just have to go and actually define all of the properties that we have available for this problem. So I'm just going to set up a small table just to capture all of the dimensions that we have. So I'm going to start by defining the nominal size for A, B, C, and D. Then I also want to give the bilateral tolerance that they specify. And then once we have the nominal size and the tolerances, then we can actually go into what the minimum size and the maximum size for each of these components will be. So I'm just going to create columns for that as well. Okay, so I think with that being done, I'm just going to say over here the feature as well, and that will then be A, B, C, and D. So we know for A that so A is this overall size that we have over here. So that is given as 44.5 millimeters. So I'm just going to say 44.5 for my nominal size. And then if I just want to increase the number of decimals, I'm just going over here saying increase decimals. So now it matches the number of decimals that I have over here. The bilateral tolerance in this case is then 0.08. So in other words, to find the minimum size, simply going to be 44.5 minus the tolerance, 0.08. And there I then get 44.42. And then on the other hand, the maximum size will simply be the nominal size plus the bilateral tolerance of 0.08. Okay, so then I can also just same for B, C, and D. So B, the nominal size is 19.05. C's nominal size is 3.05. And D is 22.23. And then I just have to give their tolerances as well. So for B, it's 0.02. For C, it's then 0.13. And finally, for D, it's 0.02. And I can just copy these functions down. So I'm just going to double click over here in the right bottom corner. Okay, so now I've populated all of the information that was given to me. Now it's only a matter of actually going and calculating this W over here. So I'm just going to say W, and then I'm also, based on the tolerance, is going to have a minimum value. So W min and W max as well. All right, so if we quickly look at how this problem is set up, we can see that A is actually equal to all of these sub features over here. So A is equal to B plus C plus D plus W. So since I have A, B, C, and D available, I'm then going to calculate W. So that will simply be equal to A minus B minus C and minus D. All right, so now I know that the nominal size for W will be 0.17. Now it's just with regards to finding W min and W max as well. So if I look at the problem over here, I expect to get the minimum value for W if A is as small as possible and B, C, D are going to be as large as possible. So this will make this little gap that I have over here the smallest possible gap. Okay, so to do that, what I can actually say for W min is I'm going to take the minimum value of A, so the minimum overall length, and then I'm simply going to minus the maximum sizes for B, C, and D. So the maximum of B minus the maximum of C minus the maximum of D. Okay, and then I can hit enter, and now I see I get minus 0.08 over here. And since this value is then smaller than 0, it means that I'm going to have interference between, I'm going to have interference. So I'm just going to say over here interference. And then for W max, so this will just be the opposite of W min. So in that case, to get the maximum gap, I'd like A to be as large as possible. And then for B, C, the values that I minus from this A to be as small as possible. So in that case, I'm going to say it's equal to the maximum size of A minus the minimum size of B and C and D. Right, so that's then 0.42, and in this case, this value is actually greater than 0, so I expect to have clearance then. Okay, so I think that sums up W min, W max. But if we look at the question again, question B actually says that we need to find basic value of D, which will assure that W is smaller than or equal to 0.08 millimeters. So what this tells us is that W min needs to be at least 0.08 millimeters. If W min is 0.08 millimeters, then my nominal size will be larger than 0.08, and W max will also be larger than that 0.08. So what I'm just going to do over there is to use, I think, the goal seek function. So if I head to the data tab, I can go what if analysis, goal seek, and then I can just the cell, in this case, it's W min. So I want to set that one equal to 0.08. The cell that I want to change is then the value of D over here. So the nominal size for D. And then if I hit OK, I can see that I now found a solution. So my target and current value match. And the value for D is then 22.07. And now I can also see W min is 0.08. So in this case, I'm then going to have a value larger than uh, 0, so that then changes to a clearance. And then W and W max are also larger than the 0.08. So this is then correct. Okay. So I hope that answers the question. So with regards to the components between which we have an interference or Pierce fit, this is actually, I think if I just quickly share my screen again. So over here, you'll see I have this component that sits around um, the nut that I have over here. So what I'm basically just saying is the gap between the bolt shoulder over here and then this hollow right circular cylindrical part. That determines where I have clearance or interference. So do I actually have a gap before the thread starts? In that case, the clearance. Otherwise, I'll have interference if this gap is actually smaller than 0. So in other words, if these cylindrical parts over here actually overlap a bit with the thread that I have. Right. Right. So we had a raised hand over here from Mr. Alex. So you can go ahead and ask the question if you'd like to use your microphone.
Okay, so my question is based off a similar question as the one that we've just done, but the question would be if there was unilateral tolerances now as well as bilateral tolerances, how would the approach to a question like that change?
Right, so the approach will mostly be the same, and I'm just going to share my screen again to illustrate this. All right, so in the case of a unilateral tolerance, so let's say, for example, we had a unilateral tolerance on B. So in other words, they perhaps say that we have plus 0, minus 0.2. So what you would do in that case is I'd rather then break up the tolerance over here. So instead of calling it an equal bilateral tolerance, I'll have upper bound, lower bound, and that will then be used to go and calculate the minimum and the maximum sizes. So once you calculated the minimum and maximum sizes based on your unilateral tolerance, then the approach will be mostly the same. So you'll still calculate W in the same way. W min will still be calculated using the minimum size of A minus the maximum sizes of B, C, and D. And then W max will be the maximum size of A minus the minimum sizes of B, C, and D. Okay, so it's just looking at what your tolerance are. So if I plus it to the nominal size, what do I get? If I minus it from the nominal size, what do I get? That will define what my maximum and minimum sizes are.
Okay, so then it would just eliminate that option of us adding all the bilateral tolerances to the nominal size for W. So we just wouldn't be able to do that then.
Yes, exactly. So if we, for example, so like I said, if we for B have, and I'm just going to type over here, let's say plus 0.0 and minus 0.02. Then I might want to do this manually. So I perhaps say that is then equal to 19.05 plus 0. And that will the minimum value will be minus 0.02. And the maximum value will then just be equal to 19.05 plus 0. Okay, so that's then how I would calculate the minimum and the maximum sizes.
Okay, cool. Thanks, sir.
Okay, not a problem.
Okay, Mr. Swanepoel is asking, the content of the exam is everything we did, but will we still discuss on Friday the structure of the exam? So the structure of the exam will be exactly the same, or similar rather. Yeah, it will be the same as the structure for the semester tests that you've written. In other words, um, there will be a design question that counts 20%. That's the distinction question. And then there's a GD&T question that will count 40% of the exam, and then 40% theory. Um, uh, and it will, that 40% theory will be divided into a 30% short questions, short questions, and then 10% a longer question. So pleasure, Mr. Swanepoel.
But Mr. Isaacs, with regards to the question on the Fenning drives and how we calculate the center distance, yes, we can quickly go through that. So once again, I'm just going to open up the spreadsheet that I made available for that as well. Right, so you'll see on ClickUp with this Fenner chain drive selection sheet over here. So to perhaps just quickly through what we did over here before we get to the center distance. Over here, I just give the design data, which we will give you in the question itself. After that, it's just a description of each of these design data points and the values that we then assign in the question. So you can go and populate this as well. And then it's simply running through all of the steps. So the service here where you can find it, design power, chain pitch, ratios, sprocket sizes, power rating. And then there are a few steps as well for question F or step F. So looking at the power rating factor, see if you have to adjust the power rating if you don't have 19 teeth on the sprocket, and then asking the question of if the power rating is greater than or equal to the design power, and then what type of chain we're using, simplex, duplex, or triplex. All right, so then it's over to question G, and then where we do the calculation for the chain length and the center distance. So you'll see in the version that I uploaded, there is already this 1006.8 millimeters, which is already the adjusted center distance. Now, if you go to table 5, you'll actually find that for the conditions that we have up here, the actual center distance or the needed center distance is 1 millimeter. So I'm just first going to pop 1000 over here. Then the pitch chain as well is found from table 5, is 25.4. And the number of teeth on the large sprocket being 38. On the small sprocket is 19. And then the factor that we have over here, so the K factor that we find table 3, is then also given as 9. So then to calculate the length of the pitches, we have this equation over here that I simply copied over from our slides as well. So what you'll notice over here is that the length of the chain in the pitches is then 100.5 pitches. Okay, but whenever we do these type of calculations, we want to round to the nearest even value, and we'd like to round up as well. So it's just what the next step does. It says the rounded length of the chain in pitches is then 108 pitches. So then what we can do is we can actually go and calculate the difference between the rounded and the unrounded value. So this is then the net over here, where I simply minus 108, or I 107.5 from the 108 over here. And then I get this 0.53 YP. Okay, so to make sure that the design that we do is indeed a valid design, we then need to go and it's the center distance until we get this difference to be 0. So in other words, our calculated of the pitches should also be 108. To do that, I can then use either goal seek or solver. I think for this problem, solver seemed to actually solve the problem. Goal seek went into a sort of a infinite loop where we tried to calculate it, and the result that we got at the end was also um, very much larger than I think the 0 value that we wanted over here for the difference. So instead, I can just make use of the solver. So I'm just heading over to the data tab again. And then over here, you should see there's an analyze ribbon or an analyze tab over here. And there should be a solver available as well. So if you don't have the solver over here, I did upload I think a website, Microsoft website you can use to load in the add-in for this solver. Okay, so if you have, then you can just click on this one, and now it's simply setting up your goal seek problem again. So we want to set this objective cell over here. So the difference in the rounded and the original chain length to the value of 0 by changing the variable cell. If we look over here, it will then be I think D53, which is this center distance over here. Right. So once I've specified that, I don't really have to change anything over here. This is basically just a more elaborate version of the goal seek, where you then go and change the solving method that you're working with as well. For this example, the RG nonlinear is sufficient. We won't expect you to use the solver in this case. So we can then just click on solve over here. Okay, so you'll see then solver gives you this error over here. Solver could not find a feasible solution. But if we actually go and check in our table, so if I just click on OK over here, you'll see that the difference in the rounded value now is 0.13 times 10 to the power of minus 5. So this is essentially 0, or very close to 0. So it means that although it couldn't find an exact solution of 0, it found something that is quite close to it. So in this case, it then updated the center distance to 1006.8 millimeters. Okay, so this is then our actual center distance, and we use the recommended center distance as sort of an initial guess for our goals that we want to perform. Okay, so if we need to repeat the actual center distance, it will be 1006.8. Right. Right. Mr. Michael, I see you said that you're struggling to find the spreadsheet ClickUp. So I just want to head over to my ClickUp as well and see where we can find. So I'm just going to share my screen again. Right. So I believe I updated. So the design material tab, firstly, I think you'll find the Finner chain drive catalogs over there. So you'll see it's the catalog used in the selection process, and then a few installation catalogs as well. And then we also have the shaft fixings over here if we want to select the taper lock bushes. With respect to the actual spreadsheet that you'll be using, should be under lecture material. And then there should be this Finner chain drives folder over there. So if you click on that one, go to spreadsheets, and you'll see it's this one over here, the Finner chain design spreadsheet revisited. Okay, so it also says over here it's a partially dynamic design spreadsheet that you can use to summarize the data you obtain from the tables or the catalogs, and use it to size and drive as well. Okay. Mr. Isaacs, with regards to your question on whether you start with the spreadsheets, yes, we will supply these in the exam. So you will have it available to populate if you want to do any chain drive designs as well. Right. With regards to this question on, I think you had a query for MSS, which was approved, you weren't awarded the mark. So I think maybe this is something that I'm also clarifying this Q&A session. So sometimes it might have we actually approve query, but even your approved value does match the marking log that you have on your side. For example, if you wrote down 5.17 and the AMS took your answer as 5 degrees 17, and you then logged the query updated again to 5.17, then you might accept that query, but log the actual answer should have been, let's say, 7.52. So the updated value still does match what is in the marking log. So my advice would be to just go and check what is the marking log that the auto grader marked according to. And if it is in the tolerance, then we can always look at that. But if it's outside the tolerance, then unfortunately there's nothing we can do. We just update the value based on whether the auto grader used an incorrect like symbol or something. Right. So I do have your, I think, mark summary available on my side as well. I've just checked it. So I do see you to write it in exponential form, but the problem is with the way you wrote it. So when you do exponential forms or you have some scientific notation that you want to write down, it's important to use the letter E to denote times 10 to the power of something. So you'll notice on your I think on your auto grader or your OCR form you also supply. If you read through the first page, which gives you the instructions on how to go about writing down different notations as well, you'll see the last example on that page actually gives you an example of how you to write the scientific notation. So in your case, you've written 2.7E9 instead of trying to write 10 to the power of 9. I think, okay, so you'll see those queries will also on the numerals. Unfortunately for those questions as well, you we don't really do partial marking when it comes to auto grading. So both value and your unit needs to be correct. So yeah, maybe just check that out and keep in mind for the upcoming exam as well.